Good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. It's December 29, 2022. It's almost New Year. Okay, my topic for tonight will be an application problem of second order differential equation. So this is now actually on my subject matter differential equation. This is now DE43. I will please I read here. DE43, meaning subject matter on differential equation, DE43, second order differential equation, and for tonight, it will be an application problem. It is similar to the so-called racket propulsion. Okay, I will try to read the problem. Okay. I cannot write the problem here, we lack space already. Even the writings on the solution, I try to minimize so it could accommodate all the part of the solution. Okay, I will try to read the problem. A body of weight W pounds, okay, moves vertically under the force of gravity and under the action of a force opposite to the direction of motion, equal numerically to a value 0.4 over 32.2 WB, where B is actually the speed in feet per second. Taking y as the distance above ground, study the motion under the conditions y equal to 0, the velocity is 100 feet per second, at time t equal to 0. Okay, I will try to summarize the problem. The problem is something like this. It seems, what do you call this? We got a spaceship. It's moving vertically upward, and according to the condition of the problem, as the rocket moves upward, there are actually two forces, what you call this, opposing its motion. And those forces are actually R, designated by R. And this is W. So anything that goes up, it should be the force of gravity. It will be pulled down by the force of gravity plus the weight of that rocket. So I place it here. It seems it's just like a rocket of the USA, mark USA over here. Okay. The resistance to motion are actually two. It's the weight, W, and R. And that R here is represented by this. Okay? The resistance to motion in terms of weight and velocity is equal to 0.4 WB over 32.2. This is under the English system, right? Because if the gravitational acceleration is 32.2 feet per second, this is under the English system. Meaning the resistance to motion is actually given by 0.4 W times the velocity over 32.2. Okay, I will shut off my alarm. Okay. It was given that the resistance to motion in terms of weight and velocity is 0.4, the product of W, the weight and velocity over 32.2. Maybe this is in pounds. Because the weight of the rocket is also in pounds. Okay? So, if I will try to give now the, what you call this illustration, this is the rocket ship. This is the resistance to motion, okay, designated by this equation here, plus the weight W. So this should be the y-axis, this is the x-axis, and this is the ground level. So at any moment in time, the height of the rocket from the ground is actually y, designated by y. Is y. So y at any moment, as it moves upward, is actually variable. Okay? And the problem is asking to study the motion, meaning we are to find y as a function of time. Okay? As the rocket moves upward, the problem is asking what will be the relation of y as a function of time. Meaning, what will be the height of that rocket at any moment in time. That's the problem asking for it. Y as a function of time. And actually, this falls under second order differential equation. Okay, let's try to bring out the solution of this. Okay? This problem now is actually, we must have to solve this in relation to Newton's law, okay? So, I place the legend over here. Weight, W is weight. The resistance to motion in terms of weight and velocity is 0.4 Wb over 32.2 in terms of pounds. And B is actually the speed of the rocket ship in terms of feet per second. Okay, and y is the variable distance of the rocket above the ground at any moment in time. So the problem is asking for, okay, y as a function of time with the given initial condition at start at time t equal to 0, y is equal to 0, and the initial speed of the rocket is 100 feet per second. This is too slow. This is just for theoretical purposes. Maybe in actual, this is 100,000 feet per second, we don't know. Okay, this is just for an example illustration, okay? So this value 100 is too small for a rocket to go up, right? This is just an illustration. If you want to be an actual thing, you make this 100,000 or 50,000. So it's possible it could go up, right? Find for y as a function of time with the given initial condition at time t equal to 0, that vertical height is 0, and the initial speed of the rocket as it fires upward is 100 feet per second. Okay? So let's try to bring out the solution. To bring out the solution of this, we will use one of the Newton's law, that is, I think, dynamics. That is, force is actually equal to mass times acceleration. Okay? This is for a moving object. Okay? So if we try to take the summation of forces along y, and we will equate that to be equal to mass times acceleration, okay? We are now on dynamics in relation to differential equations, okay? So if we try to designate that it goes up is positive, okay? This r here is going down, so this is minus r. The weight of the rocket ship is also going down, right? So this is minus W. And we should now equal to, we will follow this, the product of mass times acceleration. But what is mass under physics? Mass is actually weight over gravitational acceleration times acceleration. But what is acceleration? Okay, sorry for that one. I will erase this one so I could write the explanation of that one. Acceleration is actually d square y over dt square. Right? It's the second, because this is actually the derivative with respect to time of dy dt. And this dy dt is actually speed. If you try to take the derivative with respect to time of speed, that is acceleration. So I place it here, times d square y over dt square. That's where differential equation come out from the resulting solution. So if we now try to substitute value, the value of r in terms of weight and velocity is actually 0.4, okay, over 32.2 times the weight. For the meantime, we do not know the weight, but the weight in relation to the solution is immaterial. So I just place W here. Times, what is B? Velocity. Velocity is actually dy over dt. or this is equal to the derivative with respect to time of y. So I place it here, instead of velocity, I place it here dy dt. Minus w equal to w over 32.2 times the acceleration. I said a while ago, acceleration is the second derivative of distance with respect to time. And that variable distance for the mean time is y, right? So this is d square y over dt square. Okay? So we got now a complicated equation over here. Okay? And if you try to notice it, there is a common factor weight on each of the terms. Actually, we could remove this one by multiplying all the terms by w. Okay? And we got a 32.2 also at the bottom. So if we try to eliminate fraction, we will multiply all the terms also by 32.2. So actually, after the multiplication of 32.2 over w to the whole equation, this w here will disappear. This w here will disappear. This will become 1. And this w here will disappear. Okay, this 32.2 will be gone. This 32.2 will be gone. And this one here should be times 32.2. Okay, so what comes out is actually 0.4 times dy dt minus 32.2 equal now to the right hand side is now very clean. It is simply d square y over dt square. And if we try to rearrange this one, we will start with this. D square y over dt square. We will place this one on the right, then we try to rearrange. It will become plus, right? 0.4 dy dt. This remains on the left, but we rearrange it, so it's still negative 32.2. And this is now an SODE, a second order differential equation. That's the essence of the so-called topic second order differential equation. Meaning, after taking the summation of forces vertical on the moving rocket, okay, what comes out is actually a second order differential equation for y as a function of time. The height of the rocket at any moment in time is variable and so in time. So actually, the two variables are actually y in time. Okay? Sounds interesting? I think so, yeah. So that's the significance of this differential equation to the actual problem we are encountering today. Okay? So to solve for y as a function of time, okay, we must have to integrate 2 times, second order. So there should be a first integration. And after the first integration, there should be a second integration. Okay? And after the 2 integrations, we will compute for k1 and k2. And that's the only time that we can solve for y as a function of time. Okay, let's proceed with the solution. This one, d square y over dt square, meaning the left hand side can be written as the derivative with respect to time of the quantity dy dt plus 0.4 times y plus quantity equal to negative 32.2. Same as the one referred to under differential equation 42 yesterday, right? We eliminate, we remove this one. We put this dt here on the right hand side. Okay? Then we try to take the integral of both sides. Okay? So the integral of the differential of dy dt plus 0.4 y close quantity equal to, I bring out the negative 32.2, the integral of dt. The integral of the differential of this whole thing here, integral differential sign, they will try to cancel out each other. What will come out will just be simply dy dt plus 0.4y equal to negative 32.2 times time. The integral of the differential of time is just time plus a first constant of integration k1. So after the first integration, What comes out is a ODE, meaning a first order differential equation. Okay? Let's try to compute for the value of K1. We are given the initial condition. The problem says that at time t equal to 0, y is equal to 0, and the velocity is 100 feet per second. Okay? So at time t equal to 0, y is equal to 0, the initial velocity is 0. That initial velocity in terms of the variable height y, okay, is actually dy dt, and this is equal to 100 feet per second. So if we try to substitute dy dt to be 100, this will become, that will be 100, right? Plus 0.4, 0.4 times 0 equal to, what comes out? Negative 32.2 times 0 plus Q1. Where's Q1? Plus Q1. Good. This is 100. 0.4 times 0 will be 0. Okay. 32.2 times 0 will still be 0. So K1 will be equal to 100. So I place it there. K1 is 100. I just simplify it. I didn't write the whole simplification process. We are lacking space. Okay. So the resulting equation now will be, we now know K1. So I will rewrite the first order differential equation with the known value K1. So what comes out will be dy dt plus 0.4y equal to negative 32.2 plus 100. Okay, we are not yet given y. This is the first derivative of y with respect to time. So to solve for y as a function of time, we will try again to manipulate this one, try to integrate. Whatever integration that will come out, do it. Okay, so I place it here. And the resulting first order differential equation is similar to the form dy dt plus function of t times y equal to a q of t. Right? This was originally p of x. This is q of x. If this is dy dx, but this is in terms of time. So instead of p of x, this should be p of t and q of t. Okay, and by comparison, function of t is actually 0.4, this portion here. Right? And the integrating factor is equal to e raised to 0.4 times dt. Okay? The integral of 0.4 dt will be 0.4. The integral of dt will be just be simply t. Therefore, the needed integrating factor will be e raised to 0.4 t. This is what we need to integrate this one. And under the so-called integration of first order differential equation, solvable by using integrating factor, the general solution is actually y. Yeah, this is dy, right? So it should be y times the integrating factor equal to the integral of q of t times integrating factor multiplied by dt. Okay, so substituting values, this should be y. Integrating factor is e raised to 0.4 t equal to the integral. Q of t is actually this one here. Negative 32.2 t plus 100 closed quantity times integrating factor e to the 0.4 t times differential time. So if you try to notice it, all the terms are actually in terms of t. And we can now proceed with the integration. The only problem is, if we do not know how to integrate, let's pray that we could integrate it. So if we try to expand now, y e to the 0.4 t equal to, I will try to expand this one. What comes out will be negative 32.2, the integral of the product t times e to the 0.4 t differential time plus 100 times this. The integral of e to the 0.4 t differential time. This is easily integrable. This one, it's a product, right? So we will try to solve the integral of this separately. So we will not, prolong the solution. So to be systematic, I represent this one here to be A and this is B. So A now will be negative 32.2, the integral of t e raised to 0.4 dt. Okay? Same as yesterday, this could be solved by using integration by parts. Okay? That is, u is equal to t, du will be dt. So if u is t, what remains for dv will be e to the point 4 t dt. So for dv is actually e to the point 4 t dt. Then to compute for b, try to integrate both sides. Right? The integral of differential of b is just b equal to the integral of e to the point 4 dt. And this is now integrable. But try to bring out the correct, what they call this, differential of the exponent of e. The exponent of e is actually u is equal to 0.4 t, du will be equal to 0.4 dt. So what is lacking here is the 0.4 here. So we will introduce 0.4 here when we try to bring out 0.4 over here. So this is b now will be 1 over 0.4 e raised to 0.4 t, and 1 over 0.4 is actually 2.5 e raised to 0.4 dt. And under the so-called integration by parts, I will try to continue this one, right? Negative 32.2 times open bracket ub minus the integral of b du. That is integration by parts. By parts. Right? We now know u, we now know b, we know b and du. I try to simplify this one. Try to do it for yourself. We lack space. So after the computation of a, after the what they call this introduction of ub and the integral of b du and the simplification, what comes out for a will be negative 80.5 t a raised to 0.4 t plus 201.25 e to the 0.4 t. And for the second part, same as this integration here, what will come out will be 250 over times e to the 0.4 t. Same as the integration of this one. So to continue with the solution, y e to the 0.4 t should be equal to the sum of a plus b. I didn't show you the complete, what you call this, introduction, but if you try to put the value of a and b here, then try to simplify, what will come out here will be this. You could do it, right? The product of t e to the 0.4 t, 451.25 plus k2. There should be a second constant of integration, k2, a raised to negative 0.4 t. Then to compute for k2, apply again the given initial condition at time t equal to 0, y is 0. If you put t equal to 0 and y equal to 0 back here, then try to simplify. What comes out for the value of k2 will be negative 451.25. You place back this k2 over here, there's a common factor 451.25. So this is now 451.25 times the quantity 1 minus e raised to minus 0.4 t. But the first part is actually negative 80.5 t. So this is now y as a function of time. And what will be the significance of this? Meaning at any moment in time, if you want to find the height, you could find the height. If you say after 1 hour, you could compute for the height. Why, right? Okay? So if you specify the height also, you could compute for the time. It depends on what will be the problem is asking. But for the meantime, we now know how the rocket ship behaves when it flies. That is y is equal to negative 80.5 t plus 451.25 times the quantity 1 minus e to the minus 0.4 t. Okay guys, that's it. We got a rocket ship moving upward. At any moment in time, its height from the ground is y. Okay? And we now know y as a function of time. So choose your problem. If you specify time, you could compute for y. Okay? If you specify y, you could compute for time. You could even compute if at a height of 3 miles above ground, what will be the impact time if it hits something up. It is something like that. So that's the so-called importance of differential equation on those moving things in real life. Oh, that's it, guys. It's interesting, right? It's something like a rocket propulsion problem. So if you try to notice it, we use the summation of forces vertical. Then we try to introduce the equation of one of Newton's law, that is force is equal to ma. Okay. Moving down is the force of resistance R. Moving down is the weight of the rocket ship. So this is minus R minus W, and this should now be equal to ma. But mass is actually weight over gravitational acceleration times acceleration. The variable distance at any moment in time is y, so this should be times d square y over dt square. So what comes out is actually a second order differential equation. That's it, guys. That is one example of a problem in the application of the so-called second order differential equation. Okay, guys, for those who are taking up differential equation, these are for you guys, okay? If you like my long video, please click like. If you want to subscribe to my channel is actually at youtube.com/@profdavidj. Please click subscribe. You will get something from it. Okay, and if you want to share it to your friends, you could share it. Good evening, Los Angeles, December 29, 2022.